Hello and welcome to another lecture on mathematics for machine learning. In last lecture we introduced eigenvalues and eigenvectors and introduced a decomposition of square matrices using these eigenvectors and eigenvalues. Today we will focus more on the spectral decomposition, especially for the case of symmetric matrices. And we will discuss squared forms. So let's start. First, we define what it means for a matrix to be orthogonal. So a square matrix Q, so that is an element of R and N, is said to be orthogonal if all of its columns, so all of its n columns, are pairwise orthonormal. So they are orthogonal to each other, which means that their dot product is 0 and they are all normalized, so they have unit norm. This definition implies that, well, Q transpose Q obviously becomes the identity matrix, because each column times itself is exactly 1 and this column times another column is 0. So Q transpose Q equals the identity. But the same is true if we multiply the rows. So Q times Q transpose also is the identity. So Q transpose is the inverse of Q. This actually also means that all the rows of this matrix are pairwise orthonormal. A nice thing about these orthogonal matrices is that they preserve inner product. So if we look at the inner product between x that is multiplied by q and y that is multiplied by q, so we get another vector qx and a second vector qy, and then we do the inner product by them, then this inner product is the same as the inner product of x and y. So qx transpose times qy is the same as, remember, if we apply the transpose to the product of two terms, then the order is flipped and the transpose is applied to all the elements. So this qx transpose becomes x transpose q transpose times qy. So this becomes the identity. And we're left with x transpose y. Similarly, it also preserves the 2 norm, because the 2 norm is defined as the square root of the inner product of a vector with itself, so in this case of qx transpose times qx, and because this is the same as x transpose x, because q preserves the inner product, because it's an orthogonal matrix, this is the same as the 2 norm of x. So what we have shown is that multiplication of a vector with an orthogonal matrix preserves the norm, but it is a rotation. So it can flip the vector or change its direction, but it will always have the same norm. The trace of a matrix equals to the sum of the diagonal entries. And this trace also has some certain properties, namely that the trace of the sum of two matrices equals to the sum of the traces. It's pretty clear if we have trace of A defined as sum over the diagonal elements, aii, then of course for this it would become the sum over aii plus bii, which then can be separated in two sums, and thus one is pretty obvious that it holds. Second is that if we scale a matrix by a scalar alpha, and then take the trace of that. It's the same as taking the trace and then multiplying the trace by the same scalar alpha. I think this is also pretty clear. So if we put in alpha here, because we're multiplying A, then of course we can move this alpha in front of the sum, which is equals to alpha times trace of A. Also, very obvious is this rule that the trace of A transpose equals to the trace of A, because we're always only looking at the diagonal element, so transposition doesn't change the diagonal. And the fourth one, that's the only one that is not completely obvious, is that the trace of the product of multiple matrices allows for circular permutation. So the trace of A, B, C, D is the same as the trace of B, C, D, A, which is equals to the trace of C, D, A, B, which is equals to the trace of D, A, B, C. And this property is known as the invariance under cyclic permutation. Now note that the order in which we do this permutation is cyclic. So we cannot just do a completely arbitrary permutation of all the matrices. So we have to apply, always move the first one to the end, and so on. Also, of course, there's nothing special about 4 matrices. So we can find similar properties for more or less matrices the way we want. One rule that I want to point out that is actually quite interesting is that the trace of the matrix A is equal to the sum of the eigenvalues of the matrix. A matrix that is square, so it's n by n, is said to be symmetric if this matrix is equal to its transpose. So each element Aij is equal to Aj for any I and j. Looks quite harmless, however, it allows us to come up with a really important theorem, which is the spectral theorem. So if A is a symmetric matrix, then there exists an orthonormal basis for Rn that consists of the eigenvectors of A. The spectral theorem allows us to do a particular factorization for symmetric matrices, which is called the spectral decomposition, or also eigendecomposition, similar to the decomposition that we have seen before. However, in this case, we can use an orthonormal basis of the eigenvectors. So Q1 and Qn are orthonormal, and they are eigenvectors of A with corresponding eigenvalues lambda 1 through lambda n. Now if we form a matrix Q that holds Q1 through Qn as columns, this is an orthonormal matrix, or an orthogonal matrix, because all the vectors are orthogonal and have unit norm. And again, we build a matrix lambda. It is a diagonal matrix and has lambda 1 and to lambda n on the diagonal and zeros everywhere else. By definition, because the Qi are eigenvectors, A times Qi equals lambda I times Qi for every I. Thus, if we write this in matrix form, so remember A times, this is the same as writing Q1 through Qn equals Q1 Qn times lambda 1, lambda n, 0, 0, right? Which is the same that as if we move a in here, writing a times q1 equals q1 times lambda 1, and so on up to a times qn equals qn times lambda n. So that's just a definition of the eigenvectors and eigenvalues. So because Q is an orthogonal matrix, if we multiply this whole equation from the right by Qt, we find an interesting decomposition of A. So the right side, A Qt, QQt becomes A, as QQt is the identity matrix, cancels. The right side becomes Q lambda Qt. Now again, let A be a symmetric matrix. Then any expression x transpose A, x is called a quadratic form for a vector x and the symmetric matrix A. For quadratic forms, we can define the Rayleigh quotient as this quadratic form x transpose AX divided by the inner product of x with itself, the squared of the L2 norm of x. This Rayleigh quotient has a couple of really important properties that you should verify. So the first thing is that it is scale invariant. So for any vector that is non-zero and any non-zero scalar, the Rayleigh coefficient stays the same. If you look at the formula of the Rayleigh coefficient, this becomes pretty obvious. So please do this at home. If x is an eigenvector of A with eigenvalue lambda, then this Rayleigh coefficient is exactly equal to this eigenvalue. We build this coefficient with an eigenvector of A. This coefficient becomes the eigenvalue. An important property of the Rayleigh coefficient that we will prove soon is that it is bounded above by the largest eigenvalue of A and bounded below by the smallest eigenvalue of A. So it cannot get larger than the largest eigenvalue and cannot get smaller than the smallest. But first, let's prove a proposition that we need. So for any x that is unit norm, then the squared form x transpose AX is bounded by the smallest eigenvalue below and above by the largest eigenvalue of A. And equality only holds if x is the corresponding eigenvector of A. We will prove this theorem only for the max case. The argument for the min case is completely analogous. Because A is symmetric, we can decompose it using the spectral decomposition. So A equals Q lambda Q transpose. Now, if we do a change of variables, so remember we're looking at Q transpose AX from X to Y, where Y equals Q transpose X, then there's a one-to-one relationship between X and Y. And Y still has a norm of 1 because Q is an orthogonal matrix which preserves the norm. Now if I perform this change of variable from X to Q transpose X equals Y and write down this squared form, then it actually simplifies. Remember, this is the same as x transpose q lambda q transpose x, where this is equal to y transpose and this is equal to y. So we're left with the squared form in the diagonal matrix lambda. And because we are maximizing over x that has a norm of 1, and because this transformation preserves the norm, there is this one-to-one relationship between any x that has a unit norm and any y that has a unit norm. So if we know y, we can get x back and vice versa. So instead of maximizing over x, we can readily maximize over y in this expression. Now we know that lambda is a diagonal matrix, so we can actually write this part as a sum. So it's a sum from 1 through n over the entries of this diagonal matrix, which are all the eigenvalues of A. So it's lambda I times yi squared, because we're basically from left and right multiplying the ith entry in y. And this constraint on the norm of y is equal to saying that the squared of the norm equals 1, which means that the sum of squares of all the entries in y needs to be 1. Now that we have written this expression in this particular way, it becomes clear that in order to maximize it, subject to this constraint, we only can put non-zeros in front of the eigenvalues that are actually maximal. So in case there's only a single maximum eigenvalue, we would put that entry in y equals 1 and all the others to 0. Or if there's a multiplicity in multiple maximum eigenvalues that are equal to each other, that means that we pick out exactly these indices of the indices in lambda that correspond to the maximum eigenvalues, so to lambda max. And then we only need to look at those dimensions and which we summarize in this indicator I, and this constraint is not a sum over all of these entries of y, but only to the i's that are in this indicator or index. All the other entries in y will always be 0. And the maximum of this expression will be exactly lambda max, as we can see here. So the sum over from yi equals 1 through n lambda I yi squared for this particular maximal y simplifies as a sum only over the non-zeros of y, because all the other terms will become 0. So it's a sum over all these indices that correspond to maximum eigenvalues. So all those lambdas here that have this index are equal to lambda max, which means that we can pull this factor lambda max to the front here, because they're all equal in this case. And due to our constraint, the sum of squares of these yi's equals 1. So we're left with lambda max times the sum, which equals 1. So lambda max times 1 equals lambda max. To continue this, we now write this again as x, and remember that x equals q transpose x, and that q transpose x was our transformed y, so this equals to qy. This also equals to the yi's times qi's and the sum of that. And because all of these yi's, all the entries in y that do not correspond to lambda max are 0, we can write this matrix vector product between q and y as a sum over only these indices. So we're left with the sum over the indices corresponding to lambda max times the qi's. Remember also these qi's will be the q's corresponding to the largest eigenvalue, so they will be the eigenvectors corresponding to the eigenvalue. All our q's, our nq's, are eigenvectors of A, and they are orthogonal. And the n of them, so they are also an orthonormal basis for Rn. By construction, the set Qi that we have then forms an orthonormal basis for the eigenspace of lambda max. So any linear combination of these Qi will be an eigenvector of A that has an eigenvalue of lambda max. So what we have shown is that if we take the maximum unit norm vector of the squared form x transpose AX, we get lambda max. From this, it obviously follows that x transpose AX in general for any x will be smaller or equal to lambda max, as long as we restrict ourselves to unit length x. The maximum is lambda max, showing this as bounded above. If we did the analogous proof where we restricted ourselves to minimizing this squared form, we would have gotten lambda min, which would give us our lower bound. So x transpose AX for unit norm x is bounded above by lambda max and bounded below by lambda min. We have just proven that for unit norm x, the squared form x transpose AX is bounded above by the largest and below by the smallest eigenvalue of A. It follows immediately that the Rayleigh quotient, which is the squared form divided by x transpose x, is also bounded above by the largest eigenvalue of A and below by the smallest eigenvalue of A. Just that we can even leave out this constraint on the norm of x. So this will hold for any x, because the Rayleigh quotient is scale invariant. So the min-max theorem, which I won't prove here because that's a nice exercise for you, is that lambda min of A is smaller or equals to the Rayleigh quotient with the matrix A of x, which is smaller or equal to lambda max, the largest eigenvalue of A. And equality only holds if and only if x is a corresponding eigenvector, similar to the squared form that we have looked at before, and this holds for all non-zero x. And with this, I want to conclude for the day. So remember, we have looked at eigenvalues and eigenvectors for symmetric matrices and have shown that The spectral decomposition can be written as x lambda x transpose. We have introduced the Rayleigh coefficient, and thank you. See you next time.